Now let's look at the last example problem in this topic, not so sorted array. So we are given an array that's almost sorted. So in fact, we start with a sorted array, and then one element is randomly inserted into the array. And this may make the array no longer sorted. And we are asked to determine how many swaps are needed to make the array sorted again. So it seems difficult to sort of think about the problem in an abstract way. Let's first look at the samples input and output. So I find that to be a useful technique in general. So if a problem is hard to come up with a solution by just thinking about the abstract description, we look at the sample input and output, and we work out how to derive the sample output, and then we see whether that is a correct solution. So let's look at this array. We have 6 elements, 2, 4, 7, 7, 9, 3. So the first thing we need to do is to find out which element need to be moved. So looking at this, obviously this 3 need to be moved earlier. So why is need to be moved 3 times? Why 3 swaps are needed? So 9 needs to go to the position of 3. So 9 need to be moved backward. And 7, one of the 7s need to be moved to the position that 9 currently is. So one of the 7 need to be moved backward. 4 need to be backwards, move to one of the 7. So then 3 needs to move forward to take the position of 4. So because we need the 3 element need to move backward, and every swap can only have one element move backward, one element move forward. So 3 backward move means that we need at least 3 swaps. So it seems that what happens is we need to go from 3 up to where it's supposed to be. And because there are 3 different elements here, 3 unique elements, 4, 7, 9 here, then we need to move swap 3 times. So even if we have a more 7 or more 4 here, that doesn't seem to require additional swap, because we only need to move one of these back. So we only need to move this 7 to this 9, and then this other 7 can stay unchanged. So let's verify whether this logic is correct by looking at the next sample example. So where is this thing not sorted? So this is sorted here. So this is an element that's too big. It needs to be moved backward. It needs to be moved to here. So let's see how many different elements are in between. So 1, 2, 3, 4, 5, 6, 7. So there are 7 different unique elements in between. Each of them need to move 1 step forward. So then that means we need 7 swaps. Okay, so let's look at the last sample example. So obviously it's this guy that's not sorted. So let's see how many different elements are between these and where it need to be. 1, 2, 3, 4, 5, 6, 7. So there are 7 different unique elements in between this, and all of so that means the 7 of them need to move back. So 7 swaps. So yes, and the sample output. So that seems to be correct. So then let's implement that logic. So what I like to do is actually having some concrete example to help me explain the thinking. So let's put this input here. Okay. So we have int n and then vector. And then reading the data. Okay, so now the data has been read in, and then the next thing we need to do is to find out where the sorting relationship is broken. So we need a index variable to record where the sorting relationship is broken. So let's actually introduce the variable in the beginning and initially assigned to 0. And then we'll just looping. Let's use for loop. So we already initialized index. We don't want that. So we will be checking. We will be checking each element comparing with the next. So the last one we want to look at it a n minus 2, and we will be incrementing this. So we compare. If an element is greater than the next element, then we have find an element that is where the sorted relation is broken, and then we need to fix that. So then, what are the different conditions? So I think there are actually 4 different conditions. One of them is, in fact, the array is still sorted. That's possible because when I randomly insert an element, the array may still be sorted. So then this then that will happen when the IDX will be n minus 1. So it never broke in the middle. So it's just when it reaches the end. Then at that time, the number of swap is simply 0. And also there are cases where if I have 2 elements that are out of order, but just swapping them fix it. So that's also a possibility. Then there's a possibility that I need, like here, I need to move something multiple element earlier, and then I need to move something, and the last condition move something multi-element later. But this local swap can be merged into one of the other 2 conditions. But in order to do that, it seems I need to handle the condition where it's already sorted separately. And anyway, this is the easiest case to think about. So let's do that first. So when IDX is equal to n minus 1, that means it's already sorted. So in that case, we actually we don't really need to do anything actually, because the true answer should be 0, which should be the default case. It's an interesting way to write. So let's just keep it empty. Then what is the condition where, let's do the condition of this guy need to be moved forward. So why would this guy need to be moved forward? That must be because there has to be some other guy in front of it, and this other guy is also bigger than this. So then either swapping will move this guy backward, will not fix the problem. So then that means that this problematic index must be greater than 1. And the guy after is less than the guy earlier. So when this happens, we have no other choice. We have to move this guy to an earlier position. So move this guy. We find out how many unique elements there are until we reach someone that's less than or equal to this guy. So we'll be keep tracking of. So we need to remember this value. So because we keep comparing with it. So this is the one we are looking for. And then we are going to loop until we reach a point to insert this. And I don't think we are going to need IDX again, so we're using directly change IDX for that purpose. But we need to remember, in order to count unique elements, we need to remember the last element we saw. And we need to initialize into a value that's not equal to anything in here. So we can just use this value. So we just use this. And so there will be two conditions. So this has to be greater than this, and also AIDX has to be greater than X. So then we are still finding bigger elements, and the loop condition is IDX minus 1. And then in here, we'll be keeping track of how many unique elements we have seen. So depending on, things change when the current element is different from X. So when that happens, we have a new, we see a new element, and the last V is, so this keep track of, so but using this loop, the else should be keeping track of the number of unique element in between here and here. Okay, so that's yeah. So then the last one is, if we don't have to move this forward, then we can fix this by moving something backward. So let's actually change this example to make that. So the logic should be similar to this. So we are deciding to move AIDX backward. So this is the guy we are moving, and then we are counting how many unique elements we are seeing until we see one. So dx less than n. C value should be less than x, and then we keep adding, incrementing this. And wait, this shouldn't be x, this should be last v, which is where, because we'll keep tracking of the, if the new value is different from the last value we saw, then oh, and actually because we are moving this guy backward, we should start from IDX from here, so we need to add IDX increment by 1 here. Okay. Okay, that seems, so once we get out the loop, then we print the result. Let's see. Hey, it works. Okay, so then let's submit it. Okay, so I guess the logic is correct. Of course, yeah, I've coded a slightly different version before. Okay, so that's it for this topic.